Good morning, guys. Okay, so I wanted to make our video for arc length because I'm sorry I forgot to post that. And then I also thought it would be good for us to talk through some of these area volumes and sort of my thoughts behind them. I know that some people from first hour and then third hour kind of echoed the same thing of feeling a little bit confused on how to set it up because getting our picture going is tricky. So let's look at this first one, this warm up that we had from class today, and we have y equals e to the x. We're here. Here's e to the x, y equals e to the x. X equals 0. X equals 0 is our y axis. So it's the vertical line at x equals 0. And then y equals e cubed. Remember, e cubed is just a number. So it's just a horizontal line, e cubed, giving us this intersection point of x equals 3, y equals e cubed. 3 e cubed. Of course, this intersection point would be 0 e cubed. And then our other intersection point back here from e to the x is 0. So our region that ends up bounded is this region that's above e to the x and then below e cubed. And for part A, they ask us to rotate it around the y-axis. Okay. And so here is where all of the issues, I think, start. So the first thing we want to do is think about our picture from the dx dy situation. If I put dx in here, right, then this dx rectangle is going to rotate around like this. And so that's when I realize that I'm in the shell. If that part makes sense to you, then we're off to an awesome start. If we're confused about why it's shell, then will you guys reach out to me so that I can kind of steer my directions in a better way? Because my understanding is we're doing okay on that. I do think there's some confusion on why sometimes I will draw our dx rectangle all the way to the axis, and other times I'll draw it like this purple one that's already in there, where it's just within the area. And the difference there is if I'm dealing with a shell or if I'm dealing with a disc and washer. Remember, the shell idea is like we start here, and then as my dx circles around my axis of rotation, it starts adding on like these thicknesses. So we'll pretend that my total ending up cross-section volume thing would be this shape, right, after I've rotated it around. So the way that the shell works is I add like a layer on from the inside, and then I add another layer, and I add another layer, and I add another layer, and it's building up, right? So that this is just one of these tiny little layers popped out. And so that's the idea of how we build this is what helps me decide where R is and where H is. So for this particular little situation, R is always this distance here. R is always from our axis of rotation. So R is always measured from the axis of rotation because the radius has to come off of where we're rotating, just by definition. Which means that R is always going to be either something minus our axis of rotation, or it's going to be our axis of rotation minus something. This is or. I don't even know what to do with that. Let me change it to all caps. If I had a pen. Or, there we go. So the AOR is our axis of rotation. AOR is axis of rotation. So R is pretty much always something minus our axis of rotation, or axis of rotation minus something, because R is measured from the axis of rotation. So that's going to be one of our boundaries. Maybe that'll help us. In this case, and this was something that I remember kind of messing with my mind when I first learned these, where my little rectangle is this other sort of boundary. So if we go back over here, I imagine I put my little rectangle in here, and then I have another one and another one, and they keep moving out as we go through this integral, right? First little rectangle here, and then we have another one, and then we have another one. And as we rotate all these little rectangles around, that's what gives us our final volume, right? So let me pull some of those out of the way. So since we're rotating all those rectangles around, then we are moving our radius. Like the inside ones are going to have a smaller radius. And then as we move out to, whoops, let me undo that. I'm sorry. As we move out to the edge, then our radius is going to increase. So where this little rectangle is at any moment in time is given to us by the x coordinate. And x, x starts here, and then we go to here because that's my bounds from 0 to 3. Which I think we feel good with that 0 to 3 bounds. And then I also think, oh goodness, I think I might be good with this. I also think that we feel good with the, and I hope that this is true, that the area of each little shell is that 2 pi r h. And then the dx is like the thickness of the shell. So the dx turns it into a volume. And then we integrate to accumulate all those volumes. So then the height of my little rectangle here, that's generally a function minus another function, like top minus bottom. Like in this case, it is e to the x, e cubed minus e to the x. And I'm not sure if we follow that, but that's this idea of have this little rectangle guy, right? And I imagine him sliding through this. And usually I slide him from left to right because that's how we integrate, right? And when I'm over here on this bright boundary, that little rectangle is a little taller. And then as I move along, this end kind of gets pushed up and the rectangle gets smaller. Now the top of my rectangle is always in the same place. It has this nice flat line it travels along. But in this case, the bottom of my rectangle moves. I'm going to see that because the top of my rectangle is a constant and the bottom of my rectangle is moving. Remember, anything moving in calculus means that we have a variable there. So that's how we get the 2 pi r h dx from 0 to 3, which is really 2 pi 0 to 3. Our radius at any given time is x because it's measured from the x-axis. Then it's e cubed minus e to the x dx. This is our height. This isn't too terrible of an integral to do with your calculator. We don't know yet how to integrate x e to the x, so we can't do it by hand. So do this with your calculator and that part. I'm not concerned. So let me know if you have more questions. Hopefully that helps with the disk just a little tiny bit. I'm sorry, I just lied. Hopefully that helps with the shell a little tiny bit. I wanted to talk about the other one from the disk perspective. So then this one, we have the same picture, e to the x, e cubed, and the x equals 0, y-axis line, y equals e to the x. And then this part in here is what we're rotating. But this time, we want to rotate it around the x-axis. So then what I start thinking about is I have my little radius. Now, if I stick with dx, because my axis of rotation is here, my radius is coming in as dx. So I want to think about how this little rectangle spins. Because it's it's like this kind of thing, and I imagine here, and then this is spinning this way. So I think that you guys can see how that would make like a little imaginary, very thin disc. So I always talk about this one like from a 3D printing perspective, which I'm so glad I thought of this because we didn't have 3D printing. But from a 3D printing perspective, the disc method is like we lay down a layer and then we add another layer on top of it and a layer on top of it until we build our whole solid, right? Now these layers that we're putting down, if we look at this guy spinning, we notice that part of it is in the highlighted area, right? And then part of it is out here in this open area. So that means that after I spin this little thing around, it's actually going to make something like this. And this is like our highlighted area. So if you imagine spinning this volume around and then just looking at what this very, oh goodness, let's pretend I didn't just do that. And you just look at this very bottom part right here. The bottom of this after it was like spun around would look something like this, right? And if something like this picture right here. And if you needed to find the area of the highlighted stuff, you're like, oh, I know how to do that. I would do my big area, which this is my R. And I would subtract my small area, which is little r. And then when we think about it in terms of like what is our area, then the formula makes sense. Now, of course, if you were solving this algebraically, you could factor out the pi and do big R squared minus little r squared. But none of us have ever done that if we were using geometry to find this area, because it's just silly. But in calculus, it's super helpful for us to factor out the pi, which is why we sort of start to think we need to memorize these formulas. So remember, R is measured from our axis of rotation. So big R goes from our axis of rotation. So it's like our axis of rotation is going through there. Imagine you could see through it. From our axis of rotation out to the very outside edge, that's my big R. So that's this distance here, okay? And then big R is always going to be some function, right? Minus your axis of rotation, or we'll change that to caps. Oh, well, maybe we will if I can get an eraser. Or it's going to be our axis of rotation minus that function, right? And then little r is similar. It's also measured from our axis of rotation. So it's either going to be g of x minus our axis of rotation or our axis of rotation minus g of x. Of course, that just depends if our axis of rotation is above or in this case below, so top minus bottom, right? So hopefully that helps us understand here that our big R would be e cubed minus 0, and our little r would be e to the x minus 0. Because as we go, this is actually going to make just like a solid cylinder, this part from 0 to 3. But then this inside hollowed out part is going to be changing. That's why it has a variable in it. So e cubed squared minus e to the x squared dx. So then in class, the question came up of when do we use r squared minus r squared? Oh, no. That was not the question. We use that all the time. That's what we just did. When do you use r minus r squared? And the short answer is pretty much never, because those are radii when they're written like that. So that's not what we should be using. Instead, what you want to think about is, I'm pretty sure this confusion is coming in when we're putting in like the cross sections are perpendicular to the axis and they're like squares. And so then this area of the square is like that L squared, and that L is the top minus bottom. So just be careful when you're jumping over into your cross sections that you're not thinking about rotating anymore, and you're not thinking about the radius from the axis of rotation, that kind of thing. All right, hopefully that helps. Let me jump into arc length, and then of course we can let me know if you have questions. Let me know if you have questions about my AP, CU Succeed, or college credit, and I'll make sure to post those things as well. Okay, so arc length. So here's the whole idea of arc length. We have our wonderful arbitrary calculus function. And for whatever reason, perhaps this is like how the path that our spaceship is going to travel or whatever. I don't know. We decided that we really just can't live without knowing what is the length of that curve from like A to B? So not so much these vertical lines that I drew, but just the length along the curve. Arc length is like our perimeter sort of our function. So it's like, how far does our function go along its little path? And we're like, well, let's do this the regular calculus way. Calculus says that we zoom in until it's normal. I'm sorry, zoom in until it's linear, right? If we zoom in enough, then we realize that we can get a pretty good estimation using linear methods. And we think about, okay, well, let's pretend we're just going to measure these little tiny arc lengths, and then we'll add all the little tiny arc lengths together, because I don't know if we have computers. So we're going to say delta x is our change here, delta y is our change here. Delta y is vertical change, delta x is horizontal change. Not a big surprise there. I'm going to call this hypotenuse length L. And then the question becomes, can you guys write an equation to find L? And you're like, of course. We just use basic geometry. I know from Pythagorean theorem that delta x squared plus delta y squared is going to equal, whoops, that's supposed to be squared, is going to equal L squared. So we say, oh, good, good, good. That means that L is really the square root of whatever delta x squared plus delta y squared is. Okay? So that's lovely. Calculus says, let's let delta x get very small. So small, we're going to call it dx. Let's get delta y very small. So small, we're going to call it dy. Now right here, dx and dy are acting as like a variable. Like dx is like attached. It's not like d times x, but rather it's a single variable dx. So the total arc length, I'm going to switch this to be arc length. My arc length, which we will call L, is going to be the integral, right? Because we need to accumulate up all of these little guys of the square root of dx squared plus dy squared. Now this should give us some concern. We have this whole dx thing and dy. We shouldn't have dx or dy, and we should have some d something at the end. Or I'm sorry, we should have either dx or dy, not both of them. And we should have a d something at the end telling us which variable we're using. But we don't really have any of that. So what we're going to do is we're going to use some algebra to make this to a more reasonable formula. So here's your important takeaway. You don't need to worry about this algebra too much. Arc length comes from the Pythagorean theorem. Okay, so now let's follow along as we switch this algebra up. Okay, so our arc length, we'll call it capital L, from A to B of the square root of. And then I kind of did not do the best job of this in class, but hopefully it'll be better now. I'm going to take this dy squared and I'm going to multiply it top and bottom by dx squared over dx squared. And that's okay for me to do because dx squared over dx squared is effectively 1, right? And we can multiply by 1. That doesn't change anything. So despite the fact that it feels crazy to do that, we're going to continue. B to B, square root of dx squared plus dy squared times dx squared over dx squared. Okay? Now, so I multiplied by 1. By 1 up here. Now here what we're going to do is we're going to factor out that dx squared. Okay? So that we get L equals A to B square root of, here's my dx squared. From this term, I get a 1 plus dy squared over dx squared. Now, this is actually very good. It doesn't always feel that way, but it is. For one, we can split up our square root now, and we can take the square root of dx squared. Okay, the other thing I'm going to do is I'm going to use this property of exponents because dx and dy are acting as single variables right now. So then I get L equals a to b, the square root of 1 plus dy dx, whole thing squared. Now, this is the end of my square root, and outside of my square root is dx. And that makes us very happy because this looks like a proper integral formula. Also, we know a name for dy dx. dy dx is just the derivative of y. So here's what's super cool. If I have a function, f of x, and I want to find the arc length on some interval from a to b, then the formula for that arc length is the integral from a to b of the square root of 1 plus the derivative, so f prime of x squared dx. Okay. The big thing is we're going to have to know this formula. You're not going to need to prove it. I think it's easier to understand when you realize it came from the Pythagorean theorem, but we're going to need to use it enough that we remember it. So use to remember. It'll definitely be something that you can expect to see on the test, like find an arc length, find a perimeter, something like that. Okay, so let's do an example because I didn't get to finish all of these in class because we had a lot of important stuff to talk about. So this example is a lot like your homework, and I think I'm just going to do this one example, and I'll walk you through all the algebra on your homework. I did already post the solutions, but let's talk through it. So math teacher in me, I see arc length, and I immediately think of my integral, f prime of x squared dx, okay? And so math teacher in me goes, oh goodness, this is definitely a arc length. I definitely need to find the derivative. So let's change this x cubed over 6 plus 1 over 2x into something that's easier to take the derivative of. As in 1/6 x cubed plus 1/2 x to the -1 power. So make sure we're thinking about that, changing your functions so they're easy to take the derivative of. Then dy dx is going to be 3 over 6 x squared minus 1 over 2 x to the -2. And if you guys notice, what we have here is that we have dy dx equals 1/2 x squared minus 1/2 x to the -2. As far as your homework long term is concerned, we're going to get into a lot of gross integrals with arc length. So usually we can use our calculator. We use our calculator quite a lot for these. So it's totally okay to use your calculator. The big thing I'm worried about is the setup, but I wanted to show you this just to walk you through one so that you understood the algebra that's happening on these if you try to solve it by hand. Notice how I can factor out a half, x squared minus x to the -2. Okay. Now we said arc length was, remember, the integral from a to b of the square root of 1 plus dy dx squared dx, right? So our arc length is going to be arc length equals the integral, and we wanted to go from 1/2 to 2. 1/2 to 2. That was a little aggressive on the scrolling. Of the square root of 1 plus, and dy dx is this whole thing. So I'm going to go 1/2 x squared minus x to the -2 close squared dx. I like to put the little tail on my square roots like that so I know what's in and out of them. It was actually calculus 2 that made me switch to that because Tired of the square roots running all around. So 1 plus, I'm going to square and square. So 1/4 times x squared minus x to the negative 2 squared. I'm going to think of 1 as 4/4, and I'm also going to expand out x squared minus x to the negative 2 squared. Now, I didn't do this very well on the homework, probably because I was tired last night when I made the solutions. But what I want to think about here is as I multiply, I get x to the 4th, right? And this becomes x squared times x to the negative 2, which is just minus 1, plus x to the negative 4th, which gives me x to the 4th minus 2, plus x to the negative 4th. You follow that? So here we're at 1/2 to 2. I'm going to rewrite 1 as 4/4 plus 1/4 x to the 4th minus 2 plus x to the negative 4th dx. Okay. Part of this next move probably comes from doing a lot of math problems, but we're going to factor out 1/4. Partially because it'll get rid of our fractions, partially because 1/4 square roots nicely. It's a math problem. So if we factor out 1/4, that gives us integral from 1/2 to 2 of the square root of 1/4 times 4 from this term right here, and then all of the rest of this, plus x to the 4th minus 2 plus x to the negative 4th. Because all of this was already multiplied by 1/4, so it's, the 1/4 is just right there now. And then we can split it up, as in the square root of 1/4 and the square root of the rest of that mess. 1/2 to 2 square root of 1/4, the square root of x to the 4th plus 2 plus x to the negative 4th dx. Whoops, I'm really sorry about that. Very excessive. Okay, now, and like I said, your homework from the algebra perspective follows this pattern. This, we realize, factors. It's a perfect square. It's x squared plus x to the negative 2. It's really a lot like this one, except we have a positive in the middle. So it's going to be a lot like this, except we have a positive right there. Expand it out if you don't see it. Square root of 1/4 is 1/2. That's why there's a 1/2 out in front as a coefficient. 1/2 to 2, the square root of x squared plus x to the negative 2 squared dx. Now the reason why we have to do all this is because this square root is just a terrible thing to integrate over. So we're trying to get rid of it. When the square root falls off like that, it makes the integral way easier, which is really why we end up using a calculator so much on arc length integrals, is because there's just most of the time we're stuck with something under the square root. It's a very contrived problem, but the square root goes away. But then once you're here, this is an easy integral, right? 1/2 x cubed over 3 minus x to the, oh gosh, I add one that's -1, right? And then I divide by -1. That doesn't change anything. Evaluated from 1/2 to 2. And thank goodness, what is that? 1/2, and then we have 2 cubed over 3 minus 1/2 from x to the -1 minus 1/2 cubed over 3 minus 1/2 to the -1 is just going to be 2. And that's still terrible and gross, and I would still put that in my calculator. Let me see if I can make it look any better. 8/3 minus half. This is 1/8, and this is divided by 3, so I'm going to say that's minus 1/24, and then plus 2. All right, let's see. This is gross. We'll go to 24. 1/24 times 8, 64/24. Minus 12/24. Minus 1/24. Plus 48/24. Oh goodness, what is that? 64 Actually, if I do 48 minus 12, that's going to be 36. And if I do 36 plus 64, that's 100. And then I've taken care of these three guys. So 100 minus 1 is 99. So I'm going to go with that's 99 over 48. Check me on your calculator, see if I got that right. All right, so again, on this part, I'm totally okay with you doing it on your calculator. On the solutions, I definitely put all the plug-in in our calculator. All right, so I'm not going to worry about these other examples. Let me know if you're like really struggling and want to see them. But let's try this for our homework. All of these should follow the algebraic pattern if you want to struggle through the algebra, but really I'm most concerned with the setup is the most important. Let me know if you guys have questions and let me know if you're still struggling with disc and washer. Have a great day.